Okay, good morning. For the next few minutes, I want to share some of the work of our public-private partnership that has been directed at reducing the delivered cost of biomass feedstocks from southern pine plantations. There we go. Okay, I do want to acknowledge the co-authors on this. There are quite a few, but it's a very large project. Researchers at the U.S. Forest Service, Bob Brummer, Frank Corley, and Grant Somerville are private industry collaborators with us, and then Tom Gallagher, Matthew Smith are in the School of Forestry and Wildlife Sciences. Duran Facina, Tim McDonald are in Biosystems Engineering. Christian Broadbeck's a research engineer in our Bioenergy Center, and Brian Vai is also in the School of Forestry and Wildlife Sciences. So a very large interdisciplinary group tackling a fairly significant problem. I want to begin my comments by maybe reviving a topic that came up yesterday, and I know the speaker from DuPont mentioned this, and maybe a couple others mentioned the concept of risk. Risk is what's keeping our bioenergy industries from developing at this point, and most of that risk, I'm borrowing a little graphic from our IBIS partnership led by University of Tennessee with NC State as partners, but that risk primarily exists in the space between the biomass producer and the biorefinery. And that risk revolves primarily around the feedstock. And I would contend there's three components to that feedstock risk. One of them would be the supply. Is there adequate supply out there? And of course, the biorefinery is looking out there and saying, man, I don't want to take this leap of faith without knowing that there's a reliable supply of feedstock and at the right cost. We all know that roughly, when you look at the final gallon of fuel that comes out of that biorefinery, the final cost of that, probably half of it is due to the feedstock cost. And also quality is important. Oftentimes we hear people say, oh, it doesn't matter, I'll take any feedstock you give me, it doesn't matter what it is. Well, if you know much about conversion, I don't think you would agree. You know, you've got to have good quality feedstock. So that's the biorefinery looking at it that way, and then of course the biomass producer is saying, well, wait a minute, am I assured that if I grow this, am I assured that you're going to buy it from me? So that risk is really what's inhibiting the development of an industry today. And so as we move forward in my comments, I really kind of want to address all three of those components of that feedstock risk. And so with the end in mind, I'll just tell you right now what my main points are going to be. Essentially, that the southeast U.S. forests have the ability to supply a significant portion of our nation's biorefining feedstocks. The second one would be that new developments in logistics technologies, and by that I'm primarily going to focus on harvest and transport technologies, and we'll show that that we have reduced significantly the delivered cost of the feedstocks that will make them more affordable for the biorefineries. And then that the feedstock quality is also something that we on the logistics end can play a significant role in improving or at least affecting that feedstock quality. So those are going to be my main points. So as we go through the next few minutes, you can hopefully kind of watch how we support those. So our effort, I mentioned a public-private partnership, started about 3 years ago. The Department of Energy put out a call for proposals for what we all refer to as high tonnage logistics projects. They funded 5 of them around the United States, and they asked for consortia that would develop and demonstrate logistics technologies for feedstocks for which you could produce 100 million dry tons a year. 100 million dry tons a year is a lot. That's a pretty significant feedstock demand. And so they wanted you to be able to show them that here's the logistics technology that we can provide this level of feedstock for a biorefinery. Our contention is that the southeast U.S. is the ideal place to do that because of the existence of the forests that are here. Roughly 200 million acres of forest across the southeast. Somewhere around 30 million plus or minus acres of very highly productive pine plantations. So if we look at the theme of our conference, what's the impact of the Southeast on the world's renewable energy future? It's right here. Now, Bob, I'll defer to you. Yes, grasses are a significant part of that. All of those are part of our portfolio, but certainly you just can't ignore there's 200 million acres of highly productive forest land here. When you drill down into those forests, what are the biomass feedstocks that we might have? Frequently, we talk about forest residues. Oh, we'll just go get all the residues and use those. And there's nothing wrong with that, certainly. Short rotation hardwoods are mentioned quite frequently. And I'll maybe throw in a new one that I'll talk more about would be short rotation pine stands. So let's talk about residues real quickly. Residues, traditionally we're talking about logging residues. The primary harvesting system in southern forest would be feller buncher, grapple skidder. I'm showing the low-tech method of delimbing pine trees, which would be a delimbing gate. The skidder backs those trees through a big steel frame, and pine trees are nice. The limbs break off pretty easily, so you end up with a mountain of debris there at the landing where you're loading those logs on a truck. There are other higher-tech methods of delimbing, but essentially the same issue. You've got debris that's left frequently at the landing. That's a source of our residue. The problem with it, if you look nationwide, there's only about 50 million tons a year that we estimate could be produced there. That comes out of the billion-ton update report. So that really didn't meet DOE's demand 3 years ago for these high-tonnage systems. Our consortium backed off of that and said, let's look at something else that we could produce 100 million tons. And so we are proposing for our logistics system, it's all centered around what might be a short rotation pine plantation. And essentially what we're saying is you're going to grow a dedicated pine stand maybe 10 years, 12, maybe 15 years. It depends on your management objectives. With intensive silvicultural practices, we think you could produce 7 dry tons per acre per year. At that productivity rate, it would take about 15 million acres across the South to deliver 100 million tons a year. Out of 200 million acres of forest, we think that's doable. The benefits of that, short rotation pine plantation where you do a complete harvest of it at the end of that 10 or 12 years, one thing, your harvest productivity goes up with a complete harvest. You're not thinning, it's a complete harvest, so your productivity goes up, your delivered cost of the feedstock goes down. And then if you're the landowner, perhaps that gives you a more frequent cash flow. It depends on your management objectives, but that might give you some more options. Anecdotally, we've done some focus groups and found that, it's an interesting conclusion, we found older landowners are more willing to accept a short rotation pine plantation. I don't know if that makes sense to you, but if you're 70 years old and you're thinking, wow, I could plant some pine trees in 10 more years, I could harvest them, they can see the advantage of doing that. Younger landowners, it takes them a little bit longer to come to that conclusion. So interesting little side thing that we found. So short rotation pine plantation. Now let's talk about the logistics system that could actually harvest and transport the biomass from there. Our consortium, I'll go through them very quickly. Auburn University leads this consortium, but really a strong partnership between Auburn and the U.S. Forest Service. There's an engineering unit in Auburn that we just work hand in hand with them. And then our longtime collaborator, Corley Land Services, actually is doing the field demonstration at an industrial scale for this project. Tiger Cat is an OEM that works with us. Tiger Cat is one of the 3 major manufacturers of forest products equipment, just a great partner. The high level of management in the company, they're all engineers, and so you can sit down in a room in a few hours, you can design a new machine, and the president and CEO of the company says, okay, let's go build that. Just a great partner to work with. Precision Husky is a chipper manufacturer, and then liquid fuel partners or biorefinery partners would be Coscata, Genera, and Rentec. And then of course DOE is our primary funding agency there. So if you think about how would we harvest a system like that, I've kind of broken down logistics systems into 3 major categories. And if you look horizontally across there, in the South, most of the wood today is harvested in a traditional longwood system or tree link system. You've got a feller buncher that fells the trees, they're skidded to a landing, they're delimbed, and the entire log is loaded on a truck and transported to a refinery or a mill of some kind. One of the limitations on that is you generally cannot harvest and transport small diameter trees. The mills won't accept that small diameter material. So an alternative to that would be an in-woods chipping system where you fell it, skid it to a landing, but then chip it And so what leaves the woods would be a chip. And so it's really doesn't matter what it came from. By the time it gets to the biorefinery, they didn't know if it came from a 2-inch diameter tree or a 6-inch diameter tree. And then the final one would be something where you actually chip at the stump. And if you're familiar with some of the short rotation hardwood work, this is a photo from Tim Volk up in Syracuse, where they're actually taking an agricultural forage harvester, and then they drive through the stand and chip small diameter willow or other short rotation hardwoods. So those are 3 kind of options there. One of the things that you'll notice as you look across there, the size reduction step, the traditional sort of pulp mill mentality, if you think about those logs go to a pulp mill and then there's a large, very large chipper that does the size reduction there. Highly efficient, but capital intensive. If you look at those other options, you're taking that high capital, high horsepower machine and putting it out in the woods, or actually driving it to the stump. So in each of those, you're trading capital cost, weight, horsepower. There are lots of things that you're trading off there. What we're going to focus on, what we selected was that middle route, where we're going to take a chipper to the woods and we're going to harvest very small diameter trees, or a variety of trees, but certainly the small diameter. And so what leaves the woods would be chips in a trailer. And so again, when it gets to the refinery, you don't really care what it came from. You don't know what it came from. Now it's just in the form of chips. So our system, we changed our feller buncher. We worked with Tiger Cat to develop a new type of feller buncher that's a track type feller buncher, not the rubber tired machine. The rubber tired or wheeled feller bunchers, they actually drive to each tree in the stand. So higher site impacts. The track machine can drive down one row and then reach around it and harvest several rows around it in very low site impacts, and you're only traveling down one row instead of back and forth to every tree. So low site impacts, but it's very high efficiency. We're using a wheeled skidder, but we're really doing a lot to beef it up to just make dramatic changes in its productivity. You'll see that. In-woods chipping, we have a very high productivity disc chipper. We can make clean chips, whole tree chips, microchips, pulp-sized chips. And then in truck transport, we're going to do some work to increase the capacity of the trailers, haul more dry tons, and reduce our delivered cost. One of the techniques that we're going to use to do that is something called transpirational drying or field drying. And that's where you fell the trees but let them stay on the ground for 6 to 8 weeks. And by doing that, especially at the right time of year, you can make significant reductions in the moisture content from about 55% down to about 35%. And so when you chip that, you're hauling less water to the mill, so your dollars per dry ton transport costs can go down significantly. And if you're the biorefinery, some of them, particularly the thermochem refineries that would be purchasing Southern Pine biomass, they're going to dry the biomass anyway, so if you can do some of the drying for them, they're pretty happy about that. That reduces their operating cost and their capital cost. So our project was broken down into a R&D phase and then a really large industrial scale demonstration phase. In the R&D phase, we'll kind of go through that quickly. We did some benchmarking on traditional systems in the South, the wheel feller buncher, wheel skidder, but we did have a chipper in that system. And then we also had design activities underway. And so those design activities were both the typical mechanical design symbolized by the engineering drawing of the grapple, and then there are also sort of computer simulation design activities to look at how productive could the machine be with certain operating parameters, and then we're trying to predict cost. And through that, we were able to at least set some cost targets. We're predicting that these machines would essentially produce about 70 green tons per productive hour, and then we think we can do the total felling and skidding cost for about $4 a ton. So the challenge will be, can we actually do that? So our machines, track feller buncher, some really innovative engineering design went into it. It's an EPA Tier 4 emissions compliant engine. It's really the first machine that Tiger Cat had built that was Tier 4 compliant. We kind of backed off of convention and changed the thinking there and took the saw head off of feller buncher and put a very high-speed shear head on there. And by doing that, the saw heads that we use on most of the feller bunchers, it takes about 70 horsepower to run one of those saw heads. If you take that off, you're reducing fuel consumption. and you're reducing operating costs. It's a high maintenance item, so we're reducing operating cost, reducing fuel consumption, and reducing capital costs of the machine significantly. The felling heads, we're designing it for about a 6-inch diameter tree in those smaller diameter stands. They also put some really nifty energy recovery systems on the machine when the excavator swings and you want to stop it. It's using essentially engine braking to stop it, so the engine actually shuts off. If you listen carefully, the engine will stop firing when you want to swing and then stop. Really innovative designs, all in the name of reducing fuel consumption. So that's the machine in the field. It's been working about 1.5 years now in the field, and then you see the shear head functioned very well so far. Just to look at felling costs and productivity compared to a typical wheel feller buncher, we're consuming much less fuel per hour, higher utilization rate, and really the final number down there, the cost numbers are not significantly less, but we're doing less site impacts, less fuel consumption for a little bit less in terms of dollars per ton for the biomass. So the wheeled skidder, we took an existing skidder that Tiger Cat had and then put the largest grapple that anybody makes in the industry on it. It can skid a significant number of trees. And then they also put some ergonomic improvements on the machine. You'd think, well, doesn't everybody do that? Well, no, they didn't. The seat in the machine actually swivels. It turns around backwards with joysticks on the armrest, and so the operator can drive the machine backwards just like you can drive it forward. And so when they drive into the stand to get wood, they actually drive it backwards, and then when they get a grapple of wood, he just swivels the seat around and drives forward. That's a few seconds every time that they go out to the woods, but those few seconds add up over time. And it's all part of increasing productivity and reducing cost. The grapple, you can kind of compare it to a typical Caterpillar machine sitting next to it. It's just a monster grapple. More productivity always lowers your cost. So if you look on here, we're comparing it to a similar other brand, Skidder. Won't fuss about the other brand, but they're skidding the same distance, same time to travel back and forth, but you're skidding almost 3 times as much material. 100 tons per hour instead of 30 tons per hour. So your resulting cost for that is about 3 times less, so about $1.30 a ton to skid that. Our chipper, very high-speed disc chipper with some innovative features on it. Again, we can make multiple product types in it. And just a comparison quickly on the skidder cost and productivity, about double the productivity of traditional chippers. It costs more to operate it. It's a pretty expensive machine, about $750,000, about an 800 horsepower engine that sits there running. So it's expensive to operate, but because you increase the productivity so much, your final dollars per ton is about half or a little bit less than half. So $3.60 a ton. Transpirational drying, I mentioned that earlier. We lay the trees down and then let them stay in the stand for several weeks to reduce moisture content. That's one of the large field trials that we completed last summer. So over about a 6-week period, we reduced moisture content from 55% roughly down to about 35%. So when you do that, you're transporting less water, you're hauling less water, you're hauling more dry tons, or you have the ability to haul more dry tons. So the wood weighs less, so that let us go back and redesign the trailers that we use to design larger trailers to handle more biomass. And so a little quick spreadsheet, if you're hauling wood chips that are 56% moisture content, you chipped them today, you felled them and chipped them today, they're green, you're going to haul 28 tons roughly, net tons on that load. If they're 56% moisture content, that's 12.5 dry tons. 50-mile haul distance, about $4 per one-way mile. That works out to almost $16 a ton to transport them. And we have reduced it to 35% moisture content, you're still going to put 28 tons on there, but at 35% moisture content, you're actually hauling 18.5 dry tons now. Same basic cost to transport it, but because you're hauling more dry tons, it now is $10.78 a ton. So just by reducing the moisture content, we've reduced our haul bill by $4 a ton. It's a significant percentage there. So if you look at the overall harvest system and compare cost of a conventional system to our newer system that we developed, if you just want to do the quick answer, $24 a ton, this is all on a green ton basis, $24 a ton for that conventional system. We've shown we can reduce it down to about $13 a ton with our newer system. And then you can look at the individual components there, felling, skidding, kind of working up from the bottom. Felling would be on the bottom, skidding, loading and chipping, and then trucking is really if you look at that, trucking is probably the largest component of those costs. So we've made significant differences just in that harvest transportation cost, really almost reducing them in half with some new technology and new operating procedures. Now, I don't want to rain totally on my own parade, but to keep that in perspective, there are other costs that we don't need to forget about. And so if you look at a slightly different set of bar graphs, the very bottom blue component of both those graphs would be stumpage or a payment to the landowner. Don't forget we have to pay the landowner for this. And I know the speaker from Missouri yesterday had a much lower stumpage cost than I do, but I know this is what we're paying for wood right now. So don't forget that there's a landowner cost, there's mobilization cost, there's overhead, there's procurement cost, there's a lot of other things that go in there. But even then, we've made still a pretty significant reduction in that overall logistics delivered cost of the feedstock. Okay, our project is also looking at feedstock quality. In addition to drying and looking at moisture content as a component of that, we're also looking at other components that the biorefinery is concerned about. And there's really just one column here that I want to focus on, and that's the ash column. If we're talking about southern pine, it's primarily going to go into a thermochemical conversion plant. And so ash is a pretty significant issue. If you're running a gasifier, ash can really cause problems for you. So we've done some looking at how much ash is in southern pine as a function of how we handle it, how we harvest and transport it. And it's an interesting little set of data here. We've done just some work where we fell the trees with a feller buncher and actually carry them back to the chipper. They never touch the ground. We want to see what happens if we don't ever skid the logs. Let's just cut them off and take the feller buncher and walk back to the chipper and set them right in the chipper. So you see two rows there, one where the whole tree, that's limbs, tops, everything, and bark that's been carried to the chipper. And then there's the second row down would be delimbed and topped that go in the chipper that have been carried to the landing. And then the last one would be, let's just take wood and skid it like we normally would. Let's drag it on the ground, throw it through the chipper and look at those. And so you see that skidding function it has the ability to add a lot of ash to our feedstock. We know that by delimbing it and even debarking it, we can reduce that ash significantly, but our logistics systems can have a very significant impact on the feedstock quality, which eventually will affect the operational cost for the biorefinery. Okay. A couple other things to finish up here. We're still in the midst of a very large industrial scale demonstration. This project is actually harvesting and delivering somewhere close to 200,000 tons of wood to show at an industrial scale we can really do this. We've been testing the new machines. We've talked about transpirational drying. We're looking at extended shifts. So the upper photo there shows some nighttime operations. I think all of you would understand if you can run that machine 2 shifts during the day, one during the day and one at night, we're going to drive that cost down even farther. You're spreading those fixed capital costs out over more tons per day. So we've done some research on nighttime operations, double shifting it essentially. We're doing some work on information systems. Those are geospatial tools as well as some other information systems. And the photo there shows in the feller buncher there's a tablet computer that's inside. And TigerCat's been really good. They've allowed us, and Tim McDonald's the one that's led the work on this, they've allowed us to connect to their CAN bus on the machine, the data bus that runs all the computer systems on the machine. So they've allowed us access into that. And so by looking at when the buttons on the joysticks are pushed and looking at other functions of the machine, we can tell when the machine fells a tree, we can tell how big the tree is, we can tell where the tree is using GPS. There are lots of things that we're able to do now But one simple one is just put productivity information in front of the operator. Most of you probably have a car like mine that there's a little screen on your dashboard that tells you how many miles per gallon you're getting right now for fuel economy. That's a nice feedback mechanism to tell you to take your foot off the gas and be easy on it. Well, by putting a number on the tablet in front of that operator that tells him this is how many trees per hour you're doing right now, that's just a great motivator to maintain their productivity. So that's one of the new tools we put on there. There's other tools that are on the chipper. We just don't have time to talk about them. And the last one, we're doing some work to quantify industry and landowner acceptance. We've conducted several focus groups. Matthew Smith has done these with loggers and landowners. And so just a reminder of our little graphic image that we showed earlier, where you've got the landowner saying, you know, I might produce it if you'll buy it. You've got the biorefinery saying, well, can you produce it? You know, and that risk in the center. It's interesting, we've asked landowners, what affects your decision to produce and sell trees for conversion to energy? Essentially that short rotation pine plantation. What would affect your decision to do that? The first thing at the top of the list is the right price. Second thing is a steady market. If you look at loggers and ask them the same thing, what's going to affect your decision to buy these new systems to harvest biomass? The first thing they're going to say is market for biomass, and then availability of a long-term contract to reduce my risk. So the risk is, I guess I'm coming back to that at the end. The risk is a really critical thing here. How do we reduce the risk for the biorefinery? And we're doing that by reducing those costs of the feedstock. And that in turn reduces risk for both the logger and the landowner. So remember my three main points that we started with. We feel pretty strongly the Southeast U.S. forests can supply a significant portion of our nation's biorefining feedstocks. 200 million acres of trees can supply a lot of our biomass needs. We think that there's an opportunity for short rotation pine plantations, some dedicated energy plantations that would meet that need very well. We've shown how some new harvest and transport technologies increase productivity and reduce cost. We've made significant reductions in our harvest and transport costs, which in turn is the delivered cost of our feedstock. And then we talked a little bit about feedstock quality, both moisture content and ash. We've shown how we can manipulate those to a great extent in the field, and both of those can help or potentially hurt the biorefinery. And we think we can do a lot in the field to help the biorefinery be more successful and reduce their risk. So with that, I think we're finished.
Thanks very much, Dr. Taylor. We can take maybe one or two very quick questions. See one right down here. Microphone's coming.
Steve, great talk. One question, when you were talking about that 15 million acres supplying that 10 or 100 million, is that factoring in the 10-year rotation? It would take, so you'd have to...
Yes.
Okay.
So that's, if you look at that annual rate,
right.
you would be harvesting part of that every year. Yeah.
Okay.
Yeah.
If I understood correctly, you don't have in-field debarking. How much, if you did have that, how much additional cost do you estimate that would add?
Actually, we do, and so maybe I, in the rush of time, kind of went past that. We actually have had two debarkers that we have tested. We have a flail debarker. Big chain flail debarker, and then we have one of the chambers deliminators. If you're familiar with that, it's a similar type of debarker, but it's not quite as intensive as that flail debarker. We've run both of those, and in my little cost bar graph probably was just whole tree chips that were not debarked. If I go back and think about that, but we do have data for clean chips. We've produced clean chips with different types of delimbing technologies, so we have data for those.
One more question in the back.
Steve, thanks. Good presentation. Are those cost figures that you were showing us only what we call variable costs, or were you including capital costs also?
Yeah, that's the total machine rate. The forest engineering community uses machine rate costs, so that's everything. That's the ownership, operating cost, that's both of those.
Okay, there was one over on the side here, and we'll make this the last question.
Was there any infestation problems with the leaving the wood out for 6 to 8 weeks after you fell it?
Excellent question. Insects is what you're referring to, correct. We have data on those. Our Forest Service colleagues have collected data on insects, and you do see a rise in insect populations there, but we haven't observed any in adjacent stands. We haven't observed any negative impacts from that so far. If you think about it, a typical harvesting operation, you're going to leave debris on the site anyway, and so those insects are going to be there. They might be a little bit higher population with this because you have more material there, but so far we haven't seen any negative impacts of that on adjacent stands. Is that kind of what you're referring to? Yeah.
Okay, with that, we'll bring the first part of the session to a close.